Okay, let's start 10.5 moment of inertia calculations. So previously I said that if we can separate a rigid body or a mass distribution into its individual mass elements, then we can find the moment of inertia by summing over mi/ri squared. So the mass element times its radius or its radial position to the axis of rotation. Now that's really not always possible if we're dealing with a rigid body or a extended object. So instead what we'll need to do is take the integral. So the moment of inertia can be found by taking the integral over r squared dm. And in that sense we can use this to find the moment of inertia of any mass distribution or any object. So let's look at a few examples to see how this applies. Calculate the moment of inertia of a thin, uniform cylindrical rod of mass m and length l about a, an axis perpendicular to the rod and through the center of mass, and b, an axis of rotation perpendicular to the rod and about one end of the rod. Alright, so I've written this out for part A. Let's have a look. So it looks something like this, a thin rod, and this is the axis of rotation, which is in the center, or supposed to be in the center of the rod. Okay. So we want to take the integral. Since this rod is thin, we can assume that y equals 0 all throughout the length of the rod. So we're really only integrating over x. So we have I equals the integral of x squared dm. And now we're going to need to do a little bit of manipulating in order to have this integral over x opposed to m. So what we can do is plug in dm is rho dv. This comes just from using the formula of density equals mass over volume. So we have mass dm is density times dv, and the density is constant. That's why we can leave that in front like that. And then further from that, I want to replace dv by area times dx. Again, the cross-sectional area of this thin rod would be constant, so it's only dx that has that increment there. And then we can pull those constants out in front. So the rho a comes out in front, and we have the integral over x squared dx. At this point, I need to add in limits of integration because this is a definite integral. So it's always the range on either side of the axis of rotation. So our axis is 0 here. So this ranges from negative L over 2 to positive L over 2 on the other side. So filling those in, I have negative L over 2 and then L over 2 as the upper limit, x squared dx. And so then we can integrate, we get x cubed over 3 from L over 2, or negative L over 2 to L over 2. And at that point we can plug in that integral, so rho a over 3, I pulled out the 1/3, and then L over 2 cubed minus negative L over 2 cubed. And you can check, this will give you a factor of 1 over 12, because we'll have 1 over 8 plus 1 over 8, that's a quarter, and then times a third. So we get that 1 over 12 there. So we're at rho a L cubed over 12. So we can further replace that density times area, kind of go back to what we did at the beginning. And we have mass is density times area times the length. Since this is volume here, area times length. So notice we have density times area, and then I pull out one factor of that length and replace that with the mass. So we're left with only L squared. So our moment of inertia for this thin rod rotated about its center is 1/12 ml squared. So we do know that the moment of inertia depends on the axis of rotation, so let's try part B. Alright, so in part B we have the same thin rod, but now it's rotated about one end. So let's look at how this changes. Basically I've rewritten it, but the beginning is the same as the integral that we did in part A. We're just plugging in the density in order to find this as an integral over x opposed to m. So just to review, we plugged in dm was rho dv, and then dv is a dx, and pulled that out. So we have rho a integral over x squared dx. And this is the part where it changes. What's different now is our limits of integration. So starting at the axis of rotation, it now varies from, x varies from 0 to L. So we can take that integral from the furthest away L to 0. So the integral from 0 to L, x squared dx. And then plugging that in here and integrating again, we get x cubed over 3. And then we have row A plugging in the L cubed over 3 minus 0 for that other limit. And simplifying, again, I want to pull out one factor of row AL from here because that's the mass. So we get the mass here, and we're left with L squared. So if the axis of rotation is instead at one end of the rod, we end up with a moment of inertia of 1/3 ml squared. So a similar process has been done for many common shapes with various axes of rotation, and you can look them up in a table. I'll insert one here so you can see an example of what it would look like. And then let's try an example using one of these defined geometric shapes. Okay, example 10. Model the Earth as a uniform sphere with mass 5.97 times 10 to the 24 kilograms and radius 6.37 times 10 to the 6 meters. All right, so if we're looking at our table for a uniform sphere, this is a uniform sphere rotated about its diameter, and we find that the expression for the moment of inertia is 2/5 mr squared. So then it's really easy, just plug in the numbers from that. So these are really useful. 2/5 times the mass, 5.97 times 10 to the 24 kilograms, and then 6.37 times 10 to the 6 meters and squared. Can't really see my decimal point on the screen there. And then that gives 9.69 times 10 to the 37 kilogram meter squared. So part B asked us, how does this compare to the actual moment of inertia of the Earth? And so what we assumed when we did this was that it was a uniform sphere. So Earth is not technically a uniform sphere, not perfectly spherical in shape, and not only that, but the mass is not evenly distributed. The heavier, more dense mass is concentrated near the core, which would mean it's at a smaller radius than the outer areas of the sphere, and that would mean a lower moment of inertia. And the actual moment of inertia of the Earth is lower. You can look it up. It's about 8 times 10 to the 37 kilogram meter squared. So that's kind of interesting. Okay, we'll look at using some of these expressions in the next section.